randomly selected. I'm gonna have to write this down, but still. I really don't need to write it down. Alright. Find the probability, right? So randomly selected adult undergoes a bone density test. Find the probability of the result. Find the probability that the result is reading less than 1.27. That the probability is less than 1.27, right? Let's use our calculator. Alright. From what I know here, the result of a bone density test is commonly measured as a z-score. The result of a bone density, alright? So the z-score will be 1.27, right? These are z-scores. Okay. So then, solution. We need to find the area in figure 6-5. 6-5. Okay. Figure 6-5 below z equals 127. And it is saying find the probability that the result is reading less than 1.27. So we put the z-score of 1.27 to the right because we're trying to find something that's less than it. Okay. Below z equals 1.27. The area below z 1.27 is equal to the probability of randomly selecting a person with a bone density test result that is less than 1.27, right? The area below z 1.27 is equal to the probability of randomly selecting a person with a bone density test result that is less than 1.27. If using technology, see the instructions included at the end of this section. Alright, 1.27. If using a TA2 table, begin with the z-score of 1.27 by locating 1.2 in the left column. But this is a table, right? So I need to have a table of this. So you can't do it without a table. Okay? So then, table 1-2 begin with the z-score 1.27 by locating 1.2 on the left column. Man, can you shut the fuck up? I'll punch that dog. If using technology, alright. If using table 1-2, begin with the z-score of 1.27 by locating 1.2 in the left column. That is going to be the table A2. Alright, next find the value in the adjoining row of probabilities as directed below 0.7. So 1.2. Why is it 0.07? Why though? Alright, if using table A2, begin with the z-score 1.27 by locating 1.2. The left, why is it 1.2? Over here, example 1, right? Example 2. States population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. Mean of 0 and standard deviation of 1. So these test results meet the requirement of a standard normal distribution. Alright. Now it's asking me to find a probability that's less than 1.27. We need to find the table. Alright. But why am I finding 1.2? It's not telling me exactly why. Next, find the value in the adjoining row of probabilities that is directly below 0.07. As shown in the accompanying excerpt. Is it this? One in the past? This one isn't it, right? The probability of randomly selecting a passenger with a waiting time greater. It's a different one. Okay. Finding probabilities when given z-scores. We can find areas or probabilities for many different regions in figure 6-4 by using a T183/84 plus calculator or computer software such as StatDisk, Minitab Excel, or StatCrunch. Or we can also use table A2 in Appendix A and formulas and tablets insert card. Key features of the different methods are summarized in Table 6-1. There are. That's the formula, right? The continuous random variable has a distribution with a graph that is symmetrical and bell-shaped as figure 6-1, and it can be described by the equation given as a formula 6-1. We say that it has a normal distribution, formula 8-1. We won't actually use formula 6-1. And we include it only to illustrate that any particular normal distribution is determined by two parameters, the mean u and standard deviation 0. In that formula, the letter pi represents the constant value 3.14, and e represents the constant value 2.71. Symbols u and o represent fixed values for the mean and standard deviation, respectively. Once specific values are selected for u and o, we can graph formula 6-1, and the result will look like figure 6-1 uses for mean u and standard deviation. Fortunately, that's all we need to know about that formula. What's E though? It didn't tell me what E is. Where is E? Two times pi times that, then E. What's XU? Minus, what's E though? In this section, we develop the skills to find areas or probabilities or relative frequencies corresponding to various regions under the graph of standard normal distribution. In addition, we find z-scores. In this section, we develop the skill to find areas or probabilities or relative frequencies. All right. Corresponding to various regions under the graph I like math. A lot of students like math. What do you mean? All right. In this section, we present the standard normal distribution, which has three proportions. The graph of the standard normal distribution is bell-shaped. All right. The standard normal distribution has a mean equal to 0. That is, u is 0. And the standard normal distribution has a standard deviation equal to 1. In this section, we develop the skill to find areas corresponding to various regions under the graph of the standard normal distribution. In addition, we find z-scores that correspond to areas under the graph. These skills become important as we study on standard normal distributions and all the real important applications that we solve uniform distribution. The focus of this chapter is the concept of a normal probability distribution, but we begin with a uniform distribution. The uniform distribution allows us to see the following two very important properties. The area under the graph of the probability distribution is equal to 1. But that is, the area is equal to 1. There is a correspondence between area and probability, or relative frequencies. These are called relative frequencies, the area and probability, between the area and probability. So, some probabilities can be found by identifying the corresponding areas in the graph. By identifying the area, all right? Chapter 5 considered only discrete probability distributions, but we now consider continuous probability distributions beginning with the uniform distribution. This one is. For New York City, weekday late afternoon subway travel from Times Square to the Met Stadium. You can't take the number 7 train that leaves Times Square every 5 minutes. All right. All right, as I was saying. All right. All right. For New York City, weekday late afternoon subway travel from Times Square to the Met Stadium. You can't take number 7 train that leaves Times Square every 5 minutes. All right, number 7, and right, number 7 train, and it leaves every 5 minutes. Given the subway departure schedule and the arrival of the passenger, the waiting time X is between 0 minutes through 5 minutes, as described by the uniform distribution depicted in Figure 6-2. Note that in Figure 6-2, waiting times can be any value between 0 minutes and 5 minutes. So it is possible to have a waiting time of 2.33457 minutes. Note also that all the different possible waiting times are equally likely. The graph of a continuous probability distribution, such as Figure 6-2, is called a density curve. The density curve must satisfy the following 2 requirements. The total area under the curve must equal 1. Every point on the curve must have a vertical height that is 0 or greater. That is, the curve cannot fall between the x-axis. The curve cannot fall below. Yeah, I get it. By setting the height of the rectangle in Figure 6-2 to be 0.2, we focus the closed area to be 0.2 times 5 equals 1 to make the area equals 1, right? As required in general, the area of the rectangle becomes 1 when we make its height equal to the value of 1 range. That's 1 divided by range, man. So division. Okay, I don't have it anyways. The requirement that the area must equal 1. Alright, the area must equal 1 simplifies probability problems, so the following statement is important, and this is called uniform distribution. The other one is called the normal standard distribution, right? The standard normal distribution. It's called the uniform distribution. All right. The requirement that the area must equal 1 simplifies probability problems, so the following statement is important. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. That is important, right? The requirement that the area must equal 1, which is the middle part, is equal 1. Simplifies probability problems. So the following statement is important. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. If the area is 1, there's a correspondence between area and probability correspondence. All right. Subway waiting time. Oh no, man. I mean, fucking hold brittle. Hey, man. Don't know why they think that. They've seen me live. Okay. Given the uniform distribution illustrated in Figure 6-2, find the probability that a randomly selected passenger has a waiting time greater than 2. Okay, greater than 2, so it goes 2 to 5, right? Given the uniform distribution illustrated in Figure 6-2, find the probability that a randomly selected passenger has a waiting time greater than 2. The shaded area in 6-3 represents waiting times greater than 2 minutes. Okay. Still made 0.21 because there's 5. The correspondence, it's the area, right? 5 and 1. Okay. But then if it's greater than 2, you gotta do 2 to 5. The shaded area, yeah, I read that. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. We can find the desired probability by using areas as follows. P, which is waiting time greater than 2 minutes. Probability greater than 2 minutes, right? Area of shaded region figure. Area of shaded region 3 because 1, 2, 3. Because the maximum amount of time that it takes for the bus to get there is from 0 to 5 minutes. But they're trying to find what's from 2 minutes to 5, right? Greater than 2 minutes. 1, 2, 3. There's 3 of them, right? 3 plus 2. 3 plus 2 equals 5, yeah. So then area shaded region in figure 6-3 would be the 0.2 because the area, right? Times 3 because there's 3 times, right? Which would be 0.6. The probability of randomly selecting a passenger with a waiting time greater than 2 minutes, it's 0.6. Okay. Standard normal distribution. The density curve of a uniform distribution is a horizontal straight line, which is the density curve or standard normal distribution. What is this called? You don't have a name for it. Did you hear that guy up there in the apartments? He's saying they wanted me to treat somebody bad so I won't be able to hold my own home. Some guy named Brian, group hug, something like that. Part 101. That's kind of annoying. The density curve of a uniform distribution is a horizontal straight line. The density curve, it's called density curve, of a uniform distribution is a horizontal line. Vertical is up, down. That's horizontal. Yeah. So we find the area of any rectangular region by applying this formula. Area equals height times width. All right. Because the density curve of a normal distribution has a complicated bell shape, as shown in figure 1-6-1, it is more difficult to find areas. However, the basic principle is the same. There is a correspondence between area and probability. In figure 6-1, we show that for a standard normal distribution, the area under the density curve is equal to 1. It is not easy to manually find areas in figure 6-4. Well, wouldn't you be able to do 6 and then to make it equals 1, right? You just do that. 3 divided by 1. Oh, that's not correct. 1 divided by 3, right? It would just be like 0 points repeating 3. That would be the area, wouldn't it? Or that would not be the area. To make it 1, right? The top thing was x probability. You have 3 there. We've got to make it equal 1. That's how we found 0.2, right? By multiplying that. Multiply it times 3, right? But you know, it's kind of easier. You just divide the 1 by the 5. Wouldn't that be the right thing, right? 1 divided by 5. 0.2, right? Yeah. Yeah. Oh, I found that out by myself. Okay. But, okay. Of course, for standard normal distribution, as that, okay. The total area under its density curve is equal to 1. Okay, so area equals height times width. Because the density curve of a normal distribution has a complicated bell shape, which is this, alright? As shown in 6-1, it is more difficult to find areas. However, the basic principle is the same. There is a correspondence between area and probability. In figure 6-4, we show that for a standard normal distribution, the area under the density curve is equal to 1. It is not easy to manually find areas in figure 6-4. But we have two other relatively easy ways of finding those areas. We have two other relatively easy ways of finding those areas. Use technology or the TA2, the table A2 in Appendix A, standard normal distribution table in Appendix. Find the probability when given z-scores, when we are given these z-scores. I mean, this was a z-score, wasn't it? 5. Okay. Z-score and that. Okay. We can find areas or probabilities for many different regions in Figure 6-4 by using a T18384 plus calculator or computer software. Okay. Key features of the different methods are summarized in Table 6-1. I have these crazy neighbors in an apartment right next to me who keep screaming at me. Something about some guy named Mortali or something like that. This does get saved on my live stream, right? Key features of the different methods are summarized Table 1, okay? Because calculators or computer software generally give more accurate results than Table A2, we strongly recommend using technology. Key features of the different methods are summarized in Table 6-1 that follows. Alright. When there are discrepancies, answers in Appendix D will generally include results based on Table -2. Okay, I'm not using the table. Table 1-2. Each value in the body of the table is cumulative area from the left up to a vertical boundary above a specific z-score. When working with a graph, avoid confusion between z-scores and areas. Okay. Z-score, distance along the horizontal scale of the standard normal distribution. Refer to the leftmost column on the top row of Table A2. Z-score gives the cumulative area from the left up to the vertical line above a specific value of z. That is the z-score, right? Going on the right, but that's from left to right. Distance along, right, z-score, area, region under the curve, refer to the values in the body of table A-2. That is the z-score. I gotta read that again. Distance along the horizontal line of standard normal distribution. Refer to the left. Gives the cumulative area from the left up to a vertical line. Gives the cumulative area from the left up to a vertical line. From the left. What's the other part? The part of the z-score denoting hundredths is found across the top row A2. Bro, I can get you, bro. The body of table A. What do you mean by the body of table A? This is table A. There's two graphs, or two of them, right, man? The part of the z-score denoting hundredths is found across the top row of table A-2. Right here, what you see? Gives area bounded on the left and bounded on the right. So using the A2 table, a stat disk mini tab in Excel, they'll give you the one on the right. But if I use the calculator, it'll give me both left and right. Okay. You press the variable, right? Okay. Put second vars normal CDF. All right. Then from there, there's lower and upper, right? Then enter the two z-scores. Left z-score, right z-score. Okay, lower, upper. But this only gives you one. Okay. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis, a disease causing bones to become more fragile and more likely to break. All right, more fragile. Okay, but that's not important. The result of bone density test is commonly measured as z-score. Okay, so the results are in the z-score, not the area. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So that's 0 and that's 1. All right. Yeah, mean and standard deviation. Yeah, mean, standard deviation. It had it better right there, yeah. That's the mean, standard deviation. All right. It's like playing Pokemon. Yu-Gi-Oh! Okay. So then, these tests, all right. All right, and standard deviation of what? So these test results meet the requirements of a standard normal distribution. As long as the mean is 0 and standard deviation is 1, it meets the requirements of a standard normal distribution. Figure -4 is a graph of these results. A randomly selected adult undergoes a bone density test. Find the probability that the result is reading less than 127. So we're going to do 0 and then 127. We need to find the area in figure 6-5. We don't just make it into 1. We have to find it. Okay. Below, okay, the area, we need to find the area in figure 6-4 below z equals 1.27. The area below z equals 1.27 is equal to the probability of randomly selecting, right, the area below z, which is 1.27 here, it's equal. It is equal to the probability of randomly selecting a person with the bone density test. Result, what? The area it's equal to, all right? The area below it, below the 1.27, is equal to the probability of randomly selecting a person. Equal to the probability of randomly selecting a person with the bone density test. With the bone density test result that is less than 1.27. All right. If using technology, see the instructions included at the end of this section. If using table 1-2, begin with the z-score of 1.27 by locating 1.2. All right, man. Okay. And it did get what? I got 1.2 for the column left. Next, find the value of the adjoining row probability, which is 1.7, which leads you to 0.8980. Corresponding to z equals 1.27. So the area is 0.980. We want the area below 1.27. Yeah. And the table 1-2 gives a cumulative area from the left. So the desired area is 0.8980 because we have the correspondence between area and probability. We know the probability of a z-score below 1.27 is 0.8980. That is the probability. That's the second z-score, right? To the left, with it being below. That is the area, right? It is the area, but not the other probability. Unless, of course, it's telling me that the probability, because 1.2 and then 1.7. Because we have a correspondence between area of the probability. We know the probability of a z-score below 1.27 is, but it could have many different possibilities. That's the thing, right? Because the z-score would not be the area. It's telling me that the area is 0.8298. Another way to interpret the result is to conclude 89.80%. All right. 89.80. Okay. You always multiply times 100. One of my classmates were kind of surprised I knew that. Don't know why. It's something so easy. Anyways. The z-score is 0.07. Right? Two z-scores. It's 1.27. I messed up on that. 0.84. That is correct. Let's read that again. The area below z equals 1.27 is equal to the probability of randomly selecting a person with a bone density test result. That is, yeah, I get that, yeah. The area is below 1.27, obviously, because it's on the left. I get that, yeah. I get that. That makes sense. Yes, of course. Yeah, I get that. Okay. This is the dumb part, okay? Obviously. But that's still finding the area, right? That is a probability. So I guess you're right. It is a probability. But the previous one was a uniformal distribution graph. This is called a normal standard distribution. And this is called a bell graph for that because normal standard distributions form a bell shape, which they call the something graph. That's the name of the graph. That idiot who said, no, he's using his head. Kind of made me forget. It's on the first one. The curve is bell shaped. Alright, what do they call it again? That's a name. I want to read through all that again. I'm saying it over here, somewhere over here. Density curve. We call it density curve, right? A density curve. A bell-shaped graph is called a density curve for standard normal distributions. Density curve. All right. All right. Density curve. Density curve. That is a density curve. But there is 89.80. So then another way. Why is there right there? Anyways, right. That's the area. That's 0. Doesn't really have numbers at the bottom of the graph. So it's very different from, but this one does. That's the thing. So that is 1.27. So this wouldn't this be negative 1.27, right? Right? Wouldn't that be negative 1.27? Yeah, negative 1.27. So I could just say that another probability, without having to do all that math, would have been, well, the um, since the bell shape is the right is equivalent to the left, then I could just say negative 1.27 because that is correct. Obviously, I could also say 1, right? Anything that's way past that without doing math, because it's not really telling me to find exactly from those numbers, right? It just said less than 1.27. Obviously, I could just say 1.27. It'll still be correct realistically, because it's not asking me for a specific area, but it did say here it's equal to, right? Also, 1.26 would be less than, wouldn't it? Realistically, find the probability that the result, the result of a bone density test is commonly measured as a z-score. Yeah, the population of a z-score is normally distributed with a mean of 0 and standard deviation of 1. Yeah, so these test results meet the requirements of a standard normal distribution for 6-4. So I'm gonna check something else. So it's 0 and 1, right? And the lower is 1.27. Right. This is 7 to 9. 179. What's that other thing right there? That's 0.1. That does a big difference. Right here I get 79 point that. And if we round it up, I get 80.00, 80%. That would be correct though, right? Logically speaking. Because it's not giving anything else. I did think correctly. The mean of 0, standard deviation of 1. That says that it meets the requirement. That is correct. The area below is equal to the probability, a probability, right? It says what's a probability, not the probability. A randomly selected adult undergoes a bone density test. It's also not telling me how many, out of how many. A randomly selected adult from how many people? Like not enough data, right? All right. Anyways, let's use this. All right. Set it at the end of the section, right? Okay. So then, this. Unlike most other technologies, the T184 Plus calculator does not base areas on cumulative regions from the left. It does not base areas on cumulative regions from the left. Instead, the areas correspond to the z-score that is left boundary and another z-score that is right boundary. Second, vars, and then use normal CDF. That's what I did, alright? Proceed to enter the two z-scores. But what if they only give you one, homie? They only give you one. Alright, so I did that correctly. Proceed to enter the two z-scores separated by comma. So this is giving me a separate equation, not the same one. Proceed to enter the two z-scores separated by comma. As in left z-score and right z-score, example 5. Could be solved with the command of normal CDF minus 250, example 5, which yields a probability of 0.51 rounded. Yeah, I get that. To find a z-score corresponding to a known probability, is that going to be just 1? Yeah, too bad I don't know how to cancel this, man. To find a z-score corresponding to a known probability, press vars invo. What I did, bro. All right. Second, vars. All right. Invo norm. Area. Proceed to enter the total area to the left of the z-score. For example, the command of invo 0.97 yields a z-score of that, which is rounded to 1.96. Alright, man, but I'd like to know how to do this one. Since the book's not giving it to me. Alright, okay. Alright, man. So for this,